Okay, good morning, everybody. So today the topic is naive Bayes classifier, which we already covered partly last time, and evaluation of the classifiers. So there is we will be using this digit recognition as the example throughout this lecture mostly. In the Berkeley lecture that you were asked to watch, they classified spam versus ham emails. So there was this bag of words approach. So there was, features were words, whether they were spam or ham, and in this digit recognition, we have individual pixels. Those are our features. So it's 13 by 13. And we classify whether it's one of these digits from 1 to 9. So the output of the classifier is this digit, and it's a decision about the class or classification, and features are the pixel intensities. We had this slide already last time where we covered the Bayesian basically decision making, and so there you decided for one particular class, and that may have different costs associated with it, right? We had this example of cooking the dinner, and so that is the case, and the special case of that is use as 0 if you classify it correctly. So if the actual class is equal to the to your recognized class, and you put a penalty or cost of 1 if that is not the case, right? So it's as simple as that, the loss function. And then we looked at this. There is some math magic that by using this special case and knowing that. So this was the formula for that we use in the decision making. And now if you have this special case and you rearrange the formula, and you use the loss of probability that that they sum up to 1 for the different classes. 1 is the correct classification. These are the incorrect classifications. In this case, if you classify correctly, you know that the loss is 0. And hence, you need to consider that. And when you substitute into the formula above, and then you switch from min to max, then what you discover is that, which is not surprising, that the best you can do is that the smallest loss is for the class that is the most likely class. Okay, which is the, so you maximize over the decisions, and the winner is going to be the most probable class. So that's quite straightforward.
Excuse me.
Yes, Martin.
May I ask you? I'm sorry for interrupting you, but could you please remind me what is the delta function, delta star?
It's this one. It's right here.
Yeah.
Right. Okay. So you want me to go through the components?
Just what is the meaning of the delta function? It is because I suppose that I is sorry, delta is a loss function, and I is something like the delta, right?
So is this you mean this one? It's an L. That's the loss function. Okay.
Okay. So I just have some kind of problem with notation because I went through this in another in some another course, and it's a little bit easy for me.
No, okay, then, but I understand this is a rather complicated formula. So let's try to decode it together. Let me just go back to the notation that we used last time. So there is this. frequency, can be arbitrary, but in this case, it's simplified to the 0 to 1 case. And you have this, okay, let's write it down. So one thing that so the loss function is here, then there is the strategy, which is a mapping, which we denote here, this is delta. Okay, let me switch to writing mode. Let's do like that. So there is a strategy, which we denote with this delta, which is a mapping from the feature space, which is still, those are those observables, to decisions. In this case, 0, 1. And then there is the risk of a strategy, which is denoted here. Okay, and this is the risk of the optimal strategy, right? The star. And so for you to find it, so you're looking through the decisions or the strategies, and you're looking for the optimal one, which is minimizing this thing. And what that means is that you're minimizing the losses multiplied by this conditional probability that links the observables and the actual states. So the decision, so the loss is defined, like the rewards we had previously, based on the state and the action, right? So that's quite clear. The new thing that we're introducing here is that we don't have direct access to the states. Instead, we have access to these sort of features, and then we have to learn these probabilities from the data, typically, that link what we can perceive with what the hidden state is, right? And all these when all these come together, you're able to find the optimal strategy, right? And that's basically what we did last time. And now we just transforming it into a special case of classification of Bayesian classification in particular, which we will be looking at also today.
Yes, so we are looking for an optimal DE that minimizes the probability of other S, right?
Exactly, of misclassification, which are other classes in this case. So let's say other digits, for example.
Right.
Yeah. Okay, good. Yeah, and let's we are a small group, so we can easily make it interactive like this. I think that's good. Okay. Now, so we already mentioned that that the Bayes classification is the optimal possible. It's the optimal classifier if you have the the components that you need right. So it can also be called model based, which was mentioned in the Berkeley lecture, because you really have a model of, you have a prior what is the probability, the prior probability of the different digits, let's say, appearing, or or the spam ham thing, and you have all the components expressed as probabilities. So if you have those probabilities right, this is the best you can do. There's no other classifier, no deep network with 1,000 hidden layers that can ever do better, right? So that's kind of the theoretical conception. The practical thing, introduces some caveats, which we will look at today. So if we could get, if we could operate directly on this probability, so that means we would need a lot of training data with all these different. So this is a vector of the features. The features would be the grayscale values of individual pixels, and then you just column or row by row long vector of it. So that's your feature vector of all those pixel intensities. And if you have a lot of data, then you could have, for all the combinations, if you had it in your training data, and you would know, and then you would have it labeled, by somebody, like hand labeled, let's say, and then you could, you could simply count the frequency of the different different examples there, and this would sort of, this would be the best classifier. You could do it directly, right? Now the problem, as you may already see, is that the dimensionality is really huge, right? We will have a small quiz later, but basically you have these pixel intensities. Let's say you have from, depends what resolution we take. Imagine it was 0 to, imagine it was like 8-bit, like that, for every pixel. And so I have for every pixel I have this many options, and then I have 10 classes, and and this is gonna really grow exponentially, right? So yeah, we will have a small quiz later such that you can also try to compute it yourself. Now, so I cannot afford doing that, and moreover, practically, most of these theoretical combinations of pixel values, I will simply have no chance of encountering in any, no matter how big my data set will be. So this is not the way to go, right? I cannot, with this kind of resolution, even though the resolution is not really big, I just cannot afford doing it this way. So this would be, examples where they have, all the features have particular values and the class is a particular one. And then, you normalize it by the examples where this is the case, right? So this would be this kind of frequency, this the probability, the joint distribution over the number of times that you have seen this picture, right? And you do this for every class. Right, so this, of course, in practice, you cannot do. Yeah, and it grows exponentially with the number of pixels in images. Right, and yeah, the denominator will be often 0 because you will simply, not have a chance of seeing all these different theoretical pictures, right? So yeah, so that's not possible. Oh, and is the okay. So now to make it concrete, so just how many images are there? So a quick quiz for you. I think this is not difficult. So you can do A, B, C, D, E. Okay, so there are different opinions. Okay, so let's have a look. So if I had just one pixel, so if the resolution was, one big pixel, then how many possibilities I have of choosing the intensities? This would be 256, right? So if I had just one big pixel. Now, if I have 2 pixels, then for the first pixel, I can choose this, and for the second pixel, I can choose also this, okay? So this is the way to go. And as I have 13 by 13, which is 169 pixels, I have 256 to the power of 169 possible images, which is here, okay? And that obviously is huge, right? Even though, it's still, grayscale and the resolution is not great and everything, but it's just impossible to see all possible images and then have examples of all classes. So yeah, so this is not the way to go, right? So this is, you cannot do that. So then comes the, what we said last time, the naive Bayes classification. So the first important trick is that you use the opposite thing, right? So on this, in the end, so we are after this, right? Able to obtain in practice. Use example, this is the likelihood. This is the prior, so you have to have an idea how often the different digits occur, which you can use uniform prior, or maybe you have reasons to believe that, I don't know, zeros and ones are more likely. So if it are, if it were the zip codes, so for example, well, I actually don't know the statistics of zip codes, but yeah, it could be that some zip codes don't exist. I don't know. And then you have this evidence with which you can normalize, how often the different feature vectors come up. But as we're doing classification, this is kind of facultative, because normally after the maximum, so you don't really care about having the normalize the probability in this sense. Now, so that's one sort of trick to use the Bayes rule, and another important trick is this naive Bayes, which is here, and that is that you assume this independence. This independence doesn't hold, which is often the case in practice. That you use it like this. So this would be the whole feature vector, while here you separate it by individual components of that feature vector. So, for example, the different pixels. So what does that mean? So that means you're looking at individual pixels one by one, and you're looking at the probability that, given this pixel has a particular value, what is the probability of a particular class given that first pixel? Okay, so this would be, let's say, x00. Okay, and then you look at the next pixel and you multiply, and you do this for all classes. So this would be, let's say, 0, 1. Which is another trick that allows you to sort of deal with the curse of dimensionality, and it uses its independence assumption. And if it doesn't hold, then it's called naive, because it is naive, but it still works quite okay most of the time. Right, so that's that trick. Yeah, this we talked about. Yeah, and PS may be provided a priori, so that's the context. In a context, if it's words, there is some statistics from a dictionary. If it's the zip code, you can have some statistics. Yeah, so that, I think, is basically all we need. Right, this is the framing of the problem. So you collect data. Yeah, this we talked about. And so your goal is the optimal classification. So you're looking for to maximize this probability of the class given the data, the particular example you're supposed to. Okay, so yeah, basically unfold the two-dimensional image into one feature vector. I think in this case it's done basically column-wise. And this is really what, so the classifier basically in this case loses the idea of the of this of the topology that you see here, that it's this, and basically it just classifies it based on this long feature vector. Okay, okay, so here it is a 7. So you have these a priori digit probabilities, which may be a uniform prior, it may not be. Then running the light, this is 0 or 1 or 2, and this is a pixel at specific coordinates. So it can be, let's say, this pixel. You do it for every pixel and for every class. So you get basically tables like this. So for the class, and so this is the prior. Okay. So this is just the probability of different classes. and in this case, it's uniform. Okay. And these are the likelihoods. So this is for one. So this is pixel at 0, 0, which is this one. Now for a 7, you see that it's like a 0.1 likelihood if this pixel has this particular value, which is 25. Yeah, it's a 10% chance that it will be a 7, right? Which is quite a big chance, right? So it's because the 7 usually has this pixel here dark. So yeah, so the other classes are less likely, right? Now, yeah, so same here because it's dark around here. Now for the 0, it would be different. Most of the time, this dark kind of value in this corner for the 0 is not likely, and yeah, and this is how you set up the likelihoods from the data. And so this means that for every pixel and for every possible intensity, you create such a table, right? So still, this is still huge, right? So the problem is for all the pixel intensity, right? We have 255 of them, and so for every position, and those are 169. Yeah, you have to create that. So with this naive Bayes trick, we have just a multiplication here, right? So it's a big number, but it's we can afford to do that in a computer, right? Whereas if we didn't have this independence assumption, we would have this exponentially out of bounds. Now, so imagine we do that, and now, as you can imagine, what can happen is that for any particular position, there are these 255 possible grayscale values, right? Now, what is very likely to happen is that for some values, I don't know, for the intensity of 30 or 79 or whatever, we will just not have any example. Even if you have a big training set, it's not likely that we have seen all pixel intensities in every position. Now, what does that mean? So it means that this likelihood here for every class will be 0, right? Now, if you imagine how our classifier works, this is going to be a problem because it will just render all the. If we go back to our formula, so for class, so this is one particular pixel, right, at a specific coordinate, I don't know, 0, 1. And now for every class, this is going to be a 0, right? So that means that these for every class will be 0, right? And then we don't know, taking a max over zeros, we will basically not be able to classify. So that's a problem. So we already used some tricks, like for example, the naive independence assumption, but we need more tricks because we need to be able to, to deal with this problem of these zeros. And one of the solutions to that was also explained in the lecture from Berkeley that you were asked to watch, is the loss smoothing. So how does it work? So the probability of x, it is free. So the problem is, if that doesn't happen at all in the training set. So the trick is that you pretend to see any sample, let's say one more time, or k more times. Let's start with one more time. So that could be applied to the pixels, but in this simpler example, we'll just look at some fruits or whatever. So the trick is that so probability of X is the number of times I have seen X, which could be that the pixel at and I just add 1 to it, and to be fair, sort of, I add the 1 also to all the other intensity values, which are, so in this case, the probability of seeing this intensity value for the pixel of 25, if I have never seen it, it was here, it would be 0, but now it would be 1. Then I have the value. In this case, that's the 255, which is the okay, I didn't choose a very good example. This is 255. This can be anything, okay? So that's the number of all of the intensity values, the cardinality of that and so you do it like that. So you basically artificially blow up the data set, and in that, by doing that, you smooth it, because you will get rid. It cannot happen anymore that there will be zeros. Yeah, and it's the number of total observations, right? So this is your actual data, and this is the artificial smoothing, where you adding this 1 everywhere, even if you have an example of that, but you just want to make sure that there is at least 1 everywhere, so you're just adding it everywhere. So now, of course, it depends what is sort of the ratio of n and x. So it's small, and you okay, before doing that, a quiz. So okay, so they just had a question. What happens if in 250 do we not add? So the question, Tejas, is that if we do have an example, that whether we want to also add the 1 or not, or yeah. So we add it everywhere, because we're sort of transforming the data. So n is our actual data, and this is actually, and if we add it somewhere, then we will be sort of skewing it even more. So no, we prefer to add it everywhere, just that we have we are fair in that respect, because otherwise it would introduce another disproportionality that that would. So Martin, sound, do you still hear me okay? Okay, so let's see. So I can try to speak up. I don't know if it helps, or last part was clear. Okay, well, maybe I'll try to speak up, but yeah, do let me know if there are any problems.
Well, I think it's the problem of internet connection, because it's just sometimes we can't hear you, but it's only for a few seconds. So I guess that the upload speed just go down and then it reconnects. So I think we can't do nothing with this.
Okay, thanks. Okay, let's hope it works okay. Okay, let's first, just that you see a practical example. So imagine there are some, I don't know, fruits or, colored balls and we have, this is, and there are two red ones and one blue one. Okay, so the probability X, would be something. You just count the reds and the blues, and now the quiz for you is what would be the probability Laplacian X, by adding this artificial one to the data. So try to work on this one. This should be fairly easy. Okay, so I stop you here. Most of you have put the C. Now, what you just did, it would be the probability of X without the Laplacian, okay, without the Laplace smoothing. So, obviously, wait, no, you guys are right. No, yeah, correct. Wonderful. So sorry for my mistake. Okay, no. So this would be without the Laplacian smoothing. Okay, let's erase that. Okay, so yeah, you guys are right, and indeed it's a C. This one was, what we'll see, the number of and blues up, and this is if you add the one. So you add one to the red, which will make it 3. You add one to the blue, which will make it 2. And you have added one to the reds and one to the blues, so you have added 2 in total. You divide by 5. Yeah, so that's very easy. Right, wonderful. Okay, now the more general thing is that you may not want to add 1. You can also add k, right? Depends on because if you add 1, it's good that you don't have zeros, but you may still have very tiny probabilities, if your data is big, which, that there are also some arithmetic things involved, that, you're multiplying a lot of very small things. So you may also want to add more. Now, so what if the n, but what if you sort of overdo it, just for the sake of example? What if you use a big K, and what if n is much smaller than the K of X, K times the cardinality of X? So if you choose a big K, what are you doing to the probability distribution of X? So you have this P lap X, and here you have the different, let's say, intensities. Okay, so you initially, if you have just the data, this has some form, or it might be actually in this case a discrete probability distribution. So you have a probability mass function with some, and if you now choose a big Laplace smoothing, 1/2 for both. Lukáš says, well, it will not be 1/2. Well, it depends how many possible values there are. So what will, okay, so in this case here it's actually the digits, sorry, okay, it's not the intensities, because we're talking about 1x, which is one pixel with one value. Okay, so we have this 6 to 9, and then we have a discrete probability distribution depending how many times we have seen for that intensity that pixel intensity in the data. Some of them will be 0. Now, yeah, so what I wanted to say is that if we use a big K, then what is actually in the data will not matter anymore, and what we will end up with would be a uniform distribution, right? So in the limit, we will just basically smooth it out so much that the data will not matter anymore, because we have some few peaks and we have zeros, but then we just blow it up times x, and we will just have a uniform probability distribution. That means we will sort of suppress the training data. So that's the danger of of smoothing it too much. Yeah, so this is just well, we can do this simple quiz. I think this should be already very clear by now. So what is the cardinality of x equal to? Just the same page. So it's not. So the correct answer is C. So remember that we always denote x are always the features, right? And the but that's the S, right? So the cardinality of x is 256. Okay. Okay. Yeah. So I'm just saying that the cardinality of x is 256 because that's the feature. So x always means, that's the convention, that it's always the features, and the features are the intensity values, which are from 0 to 255, right? So two of you voted 10, but that would be the number of classes, which is S. Is it okay now, Rufa? Did you hear me? And so the next topic is we will be talking about these hyperparameters. So this is in general in machine learning. These are parameters of classification. And so this is one example. That would be the K of the Laplace smoothing. There could be many others. So for example, in regression, so regression is a sort of continuous version of classification. You're not deciding whether it's class 0 or class 1, but you're fitting basically, the output space is continuous, right? So you're fitting, these are your data points, and you're fitting a curve. So you're asking for this value on the y-axis, and that's continuous. Okay. Otherwise, it's very similar. And you could fit it with different polynomials. You can fit it with a line or with the polynomial of degree. So this is the degree of the polynomial 1, which is the straight line, degree 2, degree 3, degree 4. And this would be error on the training set. Now, the higher the degree of the polynomial, you're learning the coefficients of the polynomial. The lower the error you can achieve. You can even, with the polynomial of degree 4, you can even achieve a perfect fit. And the degree polynomial could be another higher. And the problem or the challenge in machine learning is that so you always have to trade off basically the complexity of your classifier and the complexity of the data, sort of. So the problem here is that with this degree 4 polynomial, you have a zero error on the training set, but it's what it's suffering from is overfitting. So if I happen to have another data point, which could be here, then these high degree polynomials would be off. This here I count the okay, the error is the distance here. So from so you see that the low degree polynomials, if the data points were here, have an okay error, but the high degree polynomials have a big error, right? Now, and this is already outside of the range of your training data, which may be sort of complicated. But even if I go within the data, if I have a data point here, so it's likely that what these high degree polynomials have learned was overfitting the actual data, and then with new with new testing examples, it may not work as well. So so then you need to introduce something that is called optimization, sort of penalize the for the complexity of the classifier. So in this case, the high degree of the polynomial would be penalized. It's a too complicated function to describe the data, and it's likely to overfit and not generalize. So that's a standard thing that you have to deal with in machine learning. In practice, is that you have 3 different training sets. Well, the first basic division, you need to have a training test and testing set. And so that means you have an independent testing set. So after you train your classifier, you have an independent testing set on performance. And, and then you have a sort of more realistic idea. Now, this validating set in the middle is useful in addition. It can also be called held out. So let's say you have 100 data points, which is little, but just for the sake. So, and let's say you split it up like this. Let's say 70, 15, 15. So you take one classifier with one particular, setting, let's say polynomial of some degree, and you train. Then you validate on this. And then you try a polynomial of a different degree, and again you validate. So you can use this validation set to tune the hyperparameters, let's say the type of your classifier. And once you pick the best one, then you test on the testing set. Okay, so that's how it's usually done. So it's this component. Or the Laplace smoothing of K something, or these kind of sort of structural components of your classifier, and then you have the testing set. So that's really the basics of machine learning. Yeah, so overfitting means too close to training, testing. Yeah, this is what we just spoke about. So this is data, training set, validation set, testing set. Features is attribute pairs, and the learning set. Performance on testing set. So then you have really like an independent idea how on data that you have never seen you may perform, right? And that can be quite different from the performance you achieve here, right? And more discrepancy, and then the more likely it is that you're doing overfitting, right? So if you have, let's say, 99 accuracy here, and that's not very good, right? So it could be that your classifier is complex and that, is likely to overfit. So then you might do some regularization, try something simpler, and and that's why you have this validation data set that you can tune. And then let's say you go down on the training set to 97, but you can go up to, I don't know, on the test XN to 90, and this is much better than what you had before, right? So it's better to sort of not perform as well on the training set, but what really matters is how you perform here. One way of visualizing how your classifier is doing is the confusion matrix. This is actually probably not number of times, but it seems more like a percentage. So this means the true labels, so your digits 1, 0 to 9, and this is how they were classified. And if there were 100 on the diagonal everywhere, that means you have a perfect classifier with 100% accuracy. If that is not the case, then those numbers are lower, and that you see how it really performs. In addition, this confusion matrix is called confusion matrix or confusion table because you see where the confusion occurs, right? And you can spot some interesting patterns. So here, for example, what you see is doing really badly, and it often confuses it for a 6, right? So you where the biggest problem of your current classifier is, and you can act on it. I don't know, you can so if it's an 8 and a 6, they are similar, so you can try to do something about it. I don't know, increase or something like that, but you are able to spot what the problem is. So that's a confusion matrix. And one additional important piece of analysis there are these terms. So we will look specifically at this precision and recall, but they have also synonyms. So the precision is also called true positive rate and sensitivity. So you see it now, for example, on the COVID tests, they have a particular sensitivity, and they often also have their specificity, which we will look at shortly. So the idea is that, so in this case, it's a binary classifier, okay? So COVID positive or COVID negative. So the sample you have, the real this division. So here those that actually here are here is what your classifier does. So if it labels positive, something positive, it's a true positive. If it labels positive, something that is negative, which is here, it's a false positive, right? And so like this, you can also have false negatives, things that are positive, but your classifier said they are negative, and you can also have, so you have all these different combinations, and you can have different fractions basically that describe the region in this schematics over another. So two of the most precision. Let's start with the recall. So the recall, also called the true positive rate or the sensitivity, is the ratio of this over this and that, right? So true positives over true positives and false positive. So that that seems important. If I had just that, if I want to maximize my positive, what could I do to my classifier? What would be the best classifier if I only rated it in terms of the recall. So it's the true positive rate, which is the true positive over positive, which is the true positive over true positive plus false negative. So we're talking about the recall now. 0. What do you mean 0? So what would be to maximize recall? What would be the classifier that achieves 100% in the recall?
Well, I probably didn't understand the question, so
okay.
sorry for the 0. I know that it's not correct.
No, never mind, Lukáš. Yeah, so a classifier that maximizes recall would be one that always is positive, right? So basically, you would take up the whole the complete region, and you will not make any mistakes, right? Because you will have basically this whole thing here. There will be no false negatives. You will just take up the whole thing. But of course, that's not what you want to do, because then it would have no relevance, your test, because you will just always say it's positive. That means in this case, it's good that you will never miss anything, but at the same time, that's why basically, yeah, it will not be informative. So that's why these two, the precision and the recall, are usually used in conjunction, and and together they can allow you to sort of tune the best classifier. So the precision, yeah, there's also the specificity, which is the negative over negative, which is the true negative over true negative plus false positive. So there are all these different ways of looking at it, and it takes a bit of time to digest. I also often confuse it myself, but you will have a chance to look at that during the labs, and also there is an assignment for you. So it's quite important, and people often get it wrong, and it's really relevant, as we now see with the antigen tests, and then people are asking whether this test is good or not, and this is exactly what people should look at to really and these things may have different consequences, right? So this precision and recall together, it's a sort of general thing we will see on the next slide. But as we also saw, for example, with the HIV tests, and there could be different costs with different types of mistakes, right? So if you make a false positive, or if this may have different consequences. So it may be context dependent how you design your. It may that positive, may do less harm than a false negative, right? So, for example, with the COVID tests, right? So, if you do false negative, that means somebody actually has the disease, but you label it a negative, and that's probably not what you want to do, right? It's probably better to have the opposite error, which is a false positive, and then you can send him to the PCR test, for example, if you're talking about the antigen testing. So yeah, so it may depend on the situation. And okay, so this is this ROC curve. It's for some reason historical, called receiver operating characteristics. So here is the false positive rate, which is the precision. And here is the true, which is the recall. And so I want to have, as high as possible this recall, and I want to have as low as possible the wait. So this cannot be precision. No. Yeah, okay. So this is not precision. Okay. So, sorry about that. The false positive rate is written which is false positive over everything, which is false positive over false positive plus true negative. Okay, false positive this one, and over all the. Okay, so that's the false positive rate. So from all those that do not, that do not have COVID, all those that I label that they might have, that those are my false positives. Okay, so I want to sort of minimize that. So that should go down to 0. And on the other hand, the true positive rate, which is 0. So it's very simple, right? So here is the true positives, the actually positive people are on this half, and I want to sort of, have this part of the pie as big as possible. So that's, that's what I want. And I want to have this part of the pie as small as possible. Right. So I want to minimize my green region here, and I want to minimize this red region here. And that's what is shown on this curve. So I want to go to 0 with the false positive rate, and I want to maximize my recall. And so the optimal classifier will be here, right? Which in practice you cannot attain. That's for some hyperparameters of your classifier that you might have. You can basically plot out different settings, and there's a particular point on the curve which you might, declare optimal. But again, as I said, this may depend on the context, right? You may have reasons to say that even though this would be theoretically, optimal, because of the actual context, you may want to go for a different point on the curve. But if you don't have, additional, let's say, costs associated with the decisions, this would be the optimal point from your particular classifier here. It's good to sort of practice a little bit and to get to digest this in peace. This I think I will not go into today. So the topic of next lecture will be that we look at other classifiers that are not based on probabilities. So not Bayesian classification, but but standard sort of classification that you just operate in the feature space and you try to in the feature space find some functions that separate the example, okay, like we will see next time. So this geometrical interpretation is something that belongs more to the next lecture, so a bit for there, because what we did today, this probabilistic classification, there is no there is not really any geometric interpretation. It's really based on probabilities, and you're not really operating directly in the feature space because you have these probabilities for everything. So yes, it will be more for next time. One thing that is relevant for what we learned today is that with this naive Bayes trick, you have this, these multiplications here, and the more features you have, the more things you multiply, and as you may have seen in those tables, the individual probabilities of a pixel having a particular value for a particular class may be very low, right? I don't know, something like that. And if you imagine you have, in our case, we had 169 features, but you may have more features. Something like underflow, but your computer will not be able to it will just output a 0, right? So that's not good. And so the remedy to this was also discussed in the Berkeley lecture, is that you use the laws of logs. And as you know, that the log of a product is is the log of the individual components summed up. And so that's actually that's a remedy to this problem, right? You will be summing up, and you're not risking this underflow there. So that's that's a convenient reformulation. Okay, which brings us to the end of the lecture. Right. So yeah, there was this Berkeley lecture you were asked to watch. There is also, I'll show you in a second, one specifically on Laplace smoothing if you didn't get this completely. Yeah, these are 2 textbooks that if you find them somewhere, you can use, but they are big, like full pattern recognition machine learning textbooks. So we're only covering really a small part of those. Yeah, so this is more like resources. Yeah, so that concludes the lecture. You have questions to the slides before I share the screen and we look together at the course webpage? No. Okay. So let's share the. Okay, Tejas is writing something. Okay. Okay, no, sorry about that. Now, let's share this one. Okay, so a couple of things where we are. So we're here, and there's only one more lecture to go. So, as you have seen, well, in case you are in Czech Republic now, the COVID situation is finally getting much better. But as we have one lecture to go, yeah, we're not going to change the regime, and we'll do it online as we're used to. And the plan is to do the same for the final exam. So for next time, we will do perceptrons and also KNN, so nearest neighbor classification. So please watch the lecture on perceptrons before our lecture, and also the first 16 minutes of this lecture from Berkeley, which does KNN. So we're talking about here perceptrons and then the kernels and clustering, just the first part. If there is something unclear specifically, for example, the Laplace smoothing, you can also watch a separate lecture here. Okay, and yeah, so this will be our last lecture. Now, for the exam, the dates, like the tentative dates I told you about last time, they are indeed, they have been now approved, and it's in sync with, with all the other subjects. So the regular exam date, which is the 31st of May, and 1 week later, there will be the date basically that where you could allow it, we allow you to retake it if you failed on the first date. So if it is possible, please everybody use the first date, and by doing that, you will also have an option of retaking the exam. So I hope that will work for everybody. We are not too many after all. If that doesn't work, write me as soon as possible. But really, it will be yeah, it will be great if everybody can take the exam on that date. So looking also at the at the labs, there is the classification recognition assignment, which has two parts. One is the optimal classifier, where you will write a, so Philip will correct me if I'm wrong, the naive Bayes and the KNN. And so that means the naive Bayes you already know how to do, and the KNN is something we will cover next week. The deadline for your assignment should be the 23rd. So basically we're here. We do a lecture, last lecture next week, but we also cover the KNN and perceptrons. And you will have 1 week to complete that assignment. And on the 31st is the exam date. So that means you will have basically, that week to figure out with Philip that you get the assessment, and you basically close the labs part, that you close all your exercises, and, you finalize the number of points. And then, we can, you will be allowed to sign up and take the exam. Okay. So don't leave it to the last minute. You really have to, complete the labs part, all the assessments, and the points will be finalized. And then, you can take the exam. What we will not allow is that after you take the exam, you realize, oh, I would need 2 more points. So, and then, can I redo one of the assignments from the lab? So we will not do that. Okay. So finalize your labs. You will get the final number of points. And with those, you will be taking the final exam, and, the final count will basically determine your grade. Okay. So don't leave it to the last minute, and, try to, get as many points as you are able to, and that will be your final count from the labs. Is that clear? And, and 1 week later would be the possibility for.
May I ask you about the classificators, bias and the KNN? We shall send you those classifications that are already relevant, or we just need to send you only a program, and then you will have your training data.
I will explain this in the lab in the afternoon, like explain in more detail the assignment so that it's less confusing.
Yeah,
Okay,
because I'm very confused about this last assignment, because about all the pictures and stuff like that, because I don't know how to refer to data.
Yeah, okay, no problem. I will explain this this afternoon during the lab.
Okay.
All right, thank you.
Okay, thanks, Philip. Yeah, so Philip will explain, and there are 2 parts to this assignment, which is unusual. And one is you do the actual classifier, and the other is that you determine an optimal classifier, which is more like a report, and that has to do also with the ROC curve that we covered today. But Philip will explain the details, but don't forget that it has 2 parts that you submit separately. And I think that's pretty much it. Question by Rufat in the chat. Yeah, the exam will go the same way as the midterm. Yes, indeed. It will be online. It will be this open book, and it will be longer. I think that's pretty much the only difference. I don't know yet the exact length. It may be, I don't know, an hour and a half, or maybe even 2 hours. Yeah, we have to see. But it will be a longer exam, covering the whole semester. So that, something that you already had on the midterm, plus this last block, which is basically on perception and classification. Same kind of, problem types that you can expect. And I guess that's pretty much, and we do it in the, like we're used to in the morning. So we'll probably start at 10. Because I assume that this time works for everybody. Will we be able to use notes as well? Yes, you can use notes. You can use your slides. That is all fine. What is not allowed is communicating with somebody else. It has to be your your work, but you can have, hard copy materials, and you can have also, you can have the slides also on your computer. Yeah, it will be problem solving, so there will be not many, let's say, theoretical questions. Yeah, similar like last time, you will really be asked to solve problems and apply the knowledge. Anything else? Any questions?
Maybe can I have a question about the text recognition? Maybe we will do this next week, but are there any faster way than just taking the pixels as we did it this week? Because, for example, we can, if we have number 7, we can check the edges, and I guess it will be faster than taking each pixel. Are there any other ways how to recognize text in the faster way?
Absolutely. I'm not an expert on this, but indeed, these, features, like more high-level features like edges, they have been used for a long time, and it's apparently also what the brain is using for that. So you have, and of course, then with the deep networks nowadays, basically every layer tends to sort of use features that are even more complex. So let's say, imagine you have pixels, then you have edges, then you have more complicated, let's say, geometrical things like corners, and that and that's also what has developed in the visual cortex in the brain. So yeah, and then either you can hand design those features, which was what was done sort of earlier or traditionally, and then on top of that you were using classifiers. And yeah, the big advantage of the deep networks nowadays is that you don't have to hand design the features, but they will basically learn them on their own, as they go. So yeah, and then you can sort of peek and look at the hidden layers, and if you sort of analyze it in the right way, you can even see what they learned to represent. So yes, so yeah, there's a hierarchy, and the higher up in the hierarchy, the more complex the features are.
Okay, thank you.
If we have time at the end of the lab and you ask me the question again, maybe I will be able to provide a few more details, because I did some vision recognition during my studies. So I could also.
That would be cool. That would be cool.
Okay, thank you.
Okay, wonderful. More questions? Doesn't seem to be the case. Okay, so I wish you a nice lab in the afternoon and a nice week. And yeah, next Monday will be the last online lecture. Okay, so take care and bye-bye.
Thank you. Bye.